Okay, are we on? Good morning or good afternoon, depending on your time zone. Welcome to the third installment of the CUAHSI Fall Cyber Seminar series on global to continental scale water modeling and prediction. I'd like to welcome you from the campus of Colorado School of Mines. And it's my great pleasure to introduce our speaker this week, Dr. David Gochis. Dave has an undergrad degree from KU, then went on to get his master's at Oregon State and a PhD in hydrology and water resources from the University of Arizona. Dave then moved to NCAR, where he's been staff for a number of years now and is now senior staff in RAL, the Research and Applications Lab, and has done a lot of work on understanding, both from a field perspective and from a modeling based perspective, different land atmosphere hydrometeorology type phenomena. And it's a real pleasure because Dave does a nice job in connecting both those communities and both those disciplines. Dave's done a lot of work on monsoon work in the southwestern US. He's done a lot of work on flood forecasting, in addition to model development, and has a really rich history also as a field hydrologist, which I think gives him a very nice grounded perspective when it comes to interpreting model results. Dave is, of course, also the lead developer of WRF Hydro, which is the underpinning for the U.S. National Water Model, which is going to be the topic of his talk today. So let's all virtually, even if we're clapping alone in our offices, welcome Dr. Dave Gochis. Dave, you're on.
All right. Thanks a lot, Reed. I appreciate that. There you go. You popped off. All right. So we have a screen share here. That was very generous. Definitely am glad to be here and having an opportunity to basically provide a status update on what's going on with the National Water Model. We've done some webinars in the past with CUAHSI and through a few other groups on the water model, so I don't want to be repetitive in any of this material. The one thing I do want to certainly highlight early on is this is a very sort of dynamic and broad team-based effort in the development of the National Water Model. There's a number of folks within NOAA, the Office of Water Prediction, the National Water Center, as well as our group here at NCAR, and then also in the broader community, who've made some really fundamental contributions to this effort. So, you know, I just really want to extend my appreciation and acknowledgement to all the folks who've been involved in this effort. We're going to jump right in, though, and talk about where the water model is at these days. Just a bit of background for those who haven't been up to speed on what's going on with the water model. This is an effort that was spun up within NOAA about 3 to 4 years ago as they did a number of different stakeholder engagement, survey activities, and were finding out what kinds of water prediction services either were or were not being met with their existing forecast systems. And basically came out with a diagram which looks like this, which looks at a number of different topical areas and what would be required in terms of spatial fidelity and temporal fidelity to address the issues that these stakeholders were engaged in. There's the classic problem of flood forecasting, sort of the things that are related to the protection of lives and property, which has always been at the forefront for the National Weather Service. But particularly applications of water forecasting services have really extended far beyond that. There's a lot of other groups, both in the federal agency community, local, municipal, and private sector communities that are doing a lot of other things in addition to that kind of water forecasting for applications like pollution, for water resources management, drought mitigation or adaptation strategies, and also sort of long-term issues related to management of ecosystems and biodiversity. And so when you sort of overlay all those topical areas together and try to provide people as timely as information as possible, it really points to the need for new types of forecasting systems that are sort of multi-scale and multi-temporal dimensions that allow folks to pull out information and guidance from forecast systems across a number of these different spatial and temporal scales. So that was one of the main sort of user-driven motivations for the National Water Model effort, was to try and build such a capability. So what I'm going to do then is give a quick review or a quick overview of what the system looks like. And as Reed mentioned, it's sort of the implementation of this WRF hydro modeling system over for right now, the continental domain of the United States and some tributary areas outside of that. I'll quickly go through some forecast product examples that have been either created operationally and are currently available or under development by the Office of Water Prediction, as well as some of the partner institutions. I really do want to try and highlight then some of the recent evaluations and analysis activities that have been going on as the model's been in development or in operations now for over a year, and development for a couple of years, and highlight where some of the things are, behaviors are that we've seen. Of course, we are all mobilized and extremely busy during the recent hurricane phenomenon, so I think it would be interesting to share with folks some of the products that were developed both in advance and on the fly during Hurricane Harvey just last month, and then wrap up with just really a listing of what some of the new development activities are that are going on within the National Water Model development effort, so that folks can think about different ways they may want to engage with this. Again, just highlighting here that the intention of the National Water Model effort is really to sort of build a very broad community that's contributing to this effort, that's participating in evaluation, and also getting engaged in product development for a lot of different applications. So this is the basic overview slide that we get for posterity. It's got some web links in it as well to where the National Water Model description and some documentation is listed on NOAA's website. There's a number of different things that come out of the water model, and we're going to step through those in time. The point here is that the system became fully operational just over 1 year ago in August of 2016. We had done some pre-operational testing on the Weather Service supercomputers beginning back in June of 2016, and really those were just the beginnings of this effort, and in multiple ways the system and the development has expanded, both in terms of capabilities, in terms of products and services that are being developed out of it, and in a number of partners that are sort of coming together and participating in this activity. The basic model configuration started with what was sort of traditionally the core elements of what's wrapped into the WRF hydro system in terms of physical process representation. Some of the talks that folks have seen that are more focused just on WRF hydro, we sort of break the hydrologic modeling problem up into column land surface processes, terrain routing processes to move water across and through the landscape, and then channel and reservoir routing processes. And these are sort of all linked in a framework. And for folks doing fully coupled work with the atmosphere, with atmospheric models, there's another component that extends up to the atmosphere. But this is just sort of one part of what makes a national forecasting system, which is just the core physics. What needed to be developed for the national system were a number of other components that supported real-time operations. And so starting in the upper left, this included a whole sort of forcing engine package where we're pulling in a lot of different meteorological data and weather model forecasts and preparing those for ingest into the National Water Model. There's a lot of different geospatial data processing that has to go into this to create high fidelity hydrography and surface data sets. Data assimilation is a high priority and sort of essential activity to most all operational forecasting systems, and there's a lot of different ways in which that's handled. So there was development in that area. On the other side of the periphery there, you quickly realize that model evaluation becomes a core part of the model development and improvement process. And so one of the things that was developed as part of the National Water Model effort was this open source model evaluation package written in R called our WRF Hydro that provides a number of different pathways to ingest data and extract data, ingest observational data and extract data from the National Water Model for a lot of different evaluations. And I'm going to talk quite a bit about that later because I think that's one of the key areas for additional academic engagement. Visualization services become a core part of this, and so we had adapted a number of different tools that we had in-house to provide some web mapping services for all of the different national water model outputs so that we could actually see what was going on with the model in real time. On the inside of the model physics box, you'll see that there is a new feature that was included here where we used to basically just go from the column land surface model to a high resolution routing mesh to a channel network representation. For the national water model, there was a requirement to use the national hydrography data set, the NHD Plus data set, which provided a cataloged and attributed set of catchment and river reach features for the entire nation, some 2.7 million elements that represent the nation's waterways and their tributary areas. And because that data set is used widely by so many different stakeholders, there's a strong motivation to provide this water forecasting information within that geospatial framework. And so some tools were developed that allowed for a sort of on-the-fly mapping of different runoff fields into this catchment and river network framework, and then some adaptation of the channel and reservoir routing modules to support the movement of water through that network. So those were the sort of the peripheral elements in addition to the core physics models that were implemented in the national water model that really extended this well beyond sort of the original wharf hydro system. Just to put a little bit of elaboration on what some of these spatial transformations are, this is just an example over Springfield, Missouri. I've shown this graphic in advance, but I think it's helpful for folks to get an idea of what this looks like sort of on the ground. You'll see a couple of different regular meshes here, one with solid lines, one with gridded lines. The solid lines are the 1 kilometer land surface model grid. That's the column land surface physics that are being operated and driven by meteorological data, which is remapped with some downscaling and in some cases some bias correction to that 1 kilometer grid. And then there are the dotted lines, which are a 250 meter mesh that overlays the entire country as well, which is handling the terrain routing processes, so overland flow and saturated shallow subsurface flow through the soil column. So those two meshes have two-way interactions with each other, and core runoff terms from those are then mapped into the catchments which are associated with each one of the NHD plus blue lines that you see here on this map. Now the catchments aren't illustrated on the map, but you can imagine for each one of these blue line segments that there is a tributary catchment associated with it. And so that's where that mapping occurs for both surface overland flow and subsurface runoff or soil water drainage through a base flow parameterization. And then that water is mapped back onto these river channel reaches where the channel routing and the reservoir routing does occur. So that means there's about 3 or 4 different spatial frameworks, depending on how you look at it, if you include the lake objects as well, that are being represented within the model. And there are sort of decisions that get made on what kinds of data populates those fields and what are optimal ways to go about improving and calibrating the model performance with those. This diagram here is just another view zoomed out a little bit in space to a multi-state area over the lower Mississippi River region that gives you an idea of what the spatial fidelity of the national water model is, which is sort of what's represented on all those blue line elements compared to the traditional forecasting service that's provided by the river forecast centers at those points, and how these two different systems provide sort of complementary guidance to each other, where the national water model is able to fill in some gaps and provide forecast guidance in many areas where there wasn't traditionally service, and then also sort of complement what's going on at the existing forecast points where the river forecast centers have highly calibrated models, often incorporating aspects of water management which are not currently represented in the national water model framework. This slide then summarizes what some of the data sets are that are populating the national water model at this time. We call it an NHD plus version 2 encompassing domain. So if you look in the upper right-hand panel, the terrestrial fields you see there are where the column land surface model and the terrain routing grids exist. The channel routing and the catchment mapping only occurs within those rainbow-colored tributary areas to the United States. So that's where we're getting river flow elements, and why this is sort of a NHD plus encompassing domain. There's a 1 kilometer land surface model representation. We use the NOAA MP multi-physics land surface model to represent the column processes. The land cover data set is a remapping of the 30-meter USGS National Land Cover data set. The last version of that was produced in 2011, and there's a new version that is supposed to be out about any day now, which will be incorporated into future versions of the National Water Model. We use the NRCS StatsGo data over the contiguous United States to specify soil types, and initial soil parameter estimates are derived from those soil types. There is a gridded, prescribed, sort of monthly varying vegetation map that's also overlain with this, which comes from MODIS. On the 250-meter grid, the physical processes are a diffusive wave overland flow and saturated subsurface flow, but the caveat here is that's only within the current representation of a 2-meter soil column, so we're clearly not representing deeper groundwater processes and interactions. It's really just sort of a vadose zone representation down to 2 meters. And then there's this NHD plus catchment aggregation with a fairly simple empirical base flow parameterization that's associated with that. On the NHD plus channel network, the vector network for the country, the channel routing is currently done via Muskingum-Kunj routing methodology. The reason for using that somewhat older methodology is that it is sort of inherently stable in terms of not crashing. We are required to have greater than 99.9% uptime reliability of the model, so suffering any crashes is not an option, and that presents some challenges to some of the more physically based dynamical routing methods over a channel network that's that extensive and that diverse, but there's certainly some opportunities for improving upon that. We did build some outside of contiguous United States tributaries. There's currently about 2.7 million river reaches wrapped up in the model right now, and there's about 1,500 reservoir objects which are tied into the channel network as well, which also come from the NHD plus hydrography data set. Just to step through then some of the geospatial data that's been developed. Basically that table on the left-hand side shows different versions of the model and what was added in each version in terms of the numbers of catchments or the lengths of river reaches or number of river reaches or USGS stream gauges or numbers of lakes that have been added in each successive version, getting all the way down to the total, which is there at the bottom. The map basically highlights where these different generations of tributary areas outside of the contiguous United States had to be developed as we've gone through the first 3 versions of the model here, which basically happened over the last year. That's the total number of flow lines, so you can see it's about 2.729 million river reaches across the CONUS. There's a little offset here, it looks like. I think something got corrupted a little bit in the posting of this, but you can see that in the Rio Grande data set, but these are all sort of harmonized geospatially. And then there's an overlay of the number of USGS stream gauging stations which report in real time that are available for assimilation into the model. Just to give another example here, major innovation going from version 1.1 to 1.2 of the model was a re-derivation of the gridded channel network that underlies the vector channel network in the model, so that there is more consistent harmonization between the 250-meter digital elevation model and the NHD plus vector network. That NHD plus vector network was derived based on the 30-meter NED National Elevation data set, and so when we regrid that 30-meter NED to 250 meters, there's actually distortions in the NED, and so we need to go back and rederive the gridded channel network to make it consistent at 250 meters with the vector network. And so that's been done in the latest version of the model, which is now in pre-operational testing. That's version 1.2. The practical impact of this change is that we now have a much more physically consistent depiction of the overland flow field as it's moving sort of across the landscape and into river bottom areas and into the channel network that was a bit ill-defined in some of the previous versions because of the lack of that harmonization. Okay, so as we've sort of built the underlying geospatial data sets and decided on the model physics, each one of these sort of configurations gets put into operations. There are 4 different forecast configurations of the model that exist. The main goal of having these different configurations is really to separate the forecasting problem by time. And so basically what you have is an analysis cycle in the model which keeps the model spun up to real time using observational meteorological forcing as much as possible. That basically is an hourly cycling configuration of the model driven by a merged radar and numerical weather prediction model estimate of precipitation. That analysis cycle has sort of the full physics in terms of all the routing components associated with it. The first forecast configuration then is a short-range configuration that also cycles hourly, and it runs out to 18 hours using, again, a very high-resolution numerical weather prediction model. And the main application for that is really sort of the flood and flash flood problem on the sub-daily timescales. Really one of the workhorse configurations then becomes the medium range forecast, which is driven by a coarser resolution numerical weather prediction model. And this one runs 4 times per day, so every 6 hours, but it runs out to 10 days. And so this is where we see a lot of the translation of our multi-day weather forecasts into multi-day hydrologic forecasts out to 10 days. And also we start to look at, what are some of the risks associated with flooding that are going to occur, not just in sort of the very short-term time scale, but getting out to some of the bigger river systems. And we'll show some examples of that later. There is a long-range configuration of the model as well, which is the only true ensemble configuration. It is slightly simpler in its physics configuration in that we don't do the overland flow and saturated subsurface flow routing in that configuration. We do a direct mapping of the column land surface model fields into the NHD plus catchments. So it's got a little bit different behavior associated with it, but it runs a lot faster, which allows us to do these multiple ensembles and then run out to 30 days. And it uses a different forcing data set from the NOAA's climate forecast system. Okay. This is just some technical specs then on what's wrapped up in the model. There's a lot of throughput of the model in terms of the data flow. It's a reasonably sized computational problem in terms of or system model representation or weather and climate model representation, looking at about 100,000 core hours a day of usage on the supercomputer. But like many of the other models that have been worked on and shown in this seminar series, this is sort of, not too out of line with what some other folks have been doing as well. This is just a timeline then. I won't go into all the details of this except to mention that we did go operational in that first blue box there in August of 2016 with version 1.0 of the model. Version 1.1 of the model became operational in April of this 2017 year. We also handed off version 1.2 of the model for pre-operational testing, and that is still ongoing right now. And the exact implementation date of that has not yet been decided, but it's looking like it would probably be sometime or just after the first of the year. Okay, so what are the forecast product examples that are coming from this? We've shown this animation plenty of times in the past, but it's always sort of an interesting one just to see the different kinds of weather and hydrologic processes sort of propagating through the NHD plus channel network for the nation. The fast-moving waves that you see are sort of weather systems moving across the country, causing streamflow rises, particularly in low-order stream systems. And then what you tend to see are flood waves moving more slowly, propagating more slowly behind that down some of the main stem river systems out on the Colorado. You can see the spring snowmelt pulse moving through the system and winding down, same up in the Columbia River Basin. So there's a lot of multi-scale behavior wrapped up in this. and kind of illustrates for the first time was giving the Weather Service this nationally integrated picture of these hydrologic processes. Another operational product which comes from the Office of Water Prediction is an analysis and set of forecast products for near-surface soil moisture. This is mapped in terms of the percent of saturation, and this is grabbed from this morning. So you can see that the recent wet weather there's been over the High Plains region and into the southern Front Range of the Rockies this year. There's a lot of wet soil still on the East Coast and down in Texas as a result of the recent hurricane activity. Out west, but despite the wet winter, things have dried out significantly, and to a regional degree, the water model is capturing a lot of that variability that's been going on. Another product which comes from the Office of Water Prediction is this stream flow anomaly map. So just basically a mapping of the current analyses or current forecasts from the National Water Model mapped against a long-term retrospective data set, which is basically trying to characterize average conditions on the NHD plus flow network. And you can see how this is, mapping associated with many of the variability, sort of hydrologic variability that we saw in the soils field as well. Snowpack is another key output of the model. It complements other snow products which are generated by the National Weather Service. This is a snapshot from February 7th of last year, sort of when we had a lot more extensive snow cover. You can see things across the northern plains, up into Canada and the Northeast, and then of course throughout the Intermountain West, you see a lot deeper snow values, particularly there in California, and up into the northern Rockies, which had a very wet winter last year by many measures. Another product that comes out of the model is this depth to saturation in the 2-meter soil column. Here's a snapshot of the Olympic Peninsula from May of last year, and what you see is that as a result of all the winter rains that they had in this particular region, there's a lot of saturation as indicated by the yellow colors here. Basically, the soil column at those locations in these river bottom areas is fully saturated. And then you have another behavior sort of being expressed here, which is the sort of large blue areas of saturation. And those are partially saturated soils, not fully saturated. And what that tends to underlie is where the melting snowpack was occurring at that particular time. So there's a couple of different forms of this behavior of soil saturation emerging even within this 2-meter soil column that try to account for some of the soil hydrology and its relationship in this case to either the winter rains in this area along the coastal regions or the melting snowpack. This is another field that comes out right now. This is just an image of the Grand Canyon, and I'm going to click here. Most folks should be able to see the river channel network emerging here, and you can see some slight, discontinuities with actual channels across this region. This NHD plus network certainly is not without its errors in certain areas, and you can look at that as these river vectors go sort of either up valleys, which would make sense, or sometimes right up the canyon wall, which wouldn't necessarily make sense. But that sort of gives you the idea of what's being represented here. The color coding of this is actually the channel flow velocity, which is coming out of the model. And we've been working with various folks on looking at evaluating this, how realistic it is, and what are some of the estimates of uncertainty that has in certain areas, but then also looking at how this field could be used for various applications. In the Grand Canyon area, you could think of applications related to sediment transport, to recreation, potentially some habitat. One of the examples that's also been discussed is using this river velocity field to actually trace the movement of a point source emission down the channel network, and that's what this animation here is showing. This is a post-process of the water model output where we started basically dropping a tracer in at the Gold King mine spill, which happened in 2015 in southwestern Colorado near Durango, and then that spill propagated downstream. So this is basically just a fully conservative travel time estimate and sort of map of where this constituent, this mine spill, was headed as a result of that. Now in this version, there's no mixing, there's no reactive chemistry, there's no dispersion or settling that's going on, but it is a type of product that is now available. It could be used for various applications related to some sort of point source emission like this. There's obviously a lot of work that's focused on streamflow forecasting and use of hydrographs that come out of multiple forecast cycles from the model. This is an example from some flooding that happened in the springtime in northeastern Oklahoma. The observations here are in black. The water model actually did a pretty good job of this in terms of hitting the peak flow, but it was several hours in advance for multiple cycles. And that's really one of the pathological behaviors we've seen in the model, is that it tends to propagate flood waves too fast and with too sharp of a behavior in terms of its hydrographic response. One of the main reasons for that are some uncertainties in the channel parameters associated with the NHD Plus network and their implementation of the Muskingum-Kunj method, but also the fact that we don't have overbank flow occurring in the model yet, which would attenuate some of these flood wave processes. And so that is a core development activity for the next version of the model, is to include that two-way interactions with the overland flow fields. There's another field which comes out of the model, which is the surface overland flow depth, or sometimes it's called ponded water, and that could be used in some ways as guidance for where certain flooding risks might occur. This is also from last spring, where there was, for folks in the Midwestern United States, remember this period as being excessively wet throughout parts of Missouri and into southern Illinois. This is basically some analyses and then short-range forecasts of this surface overland flow field across this region. And then what you see here are what the local storm reports were and the flash flood warnings that were issued by the Weather Service associated with some of this heavy rainfall, and where those warnings and storm reports overlied the model representation, forecast, or analysis of where water was piling up on the land surface. It's really difficult as folks, we've got feedback from forecasters and a lot of other folks to sort of digest all of this river network information at once. And so there's a lot of work going on within the Office of Water Prediction and the National Water Center now to provide synthesis products of streamflow forecasts. And one of these is looking at the probability of high flow across the channel network over a certain time frame, say over the next 12 hours or so. This particular graphic here is providing that. It's basically showing what is the probability of flow exceeding a certain threshold based on a number of different overlapping forecasts that were generated from the short-range configuration of the model. And here you can see that in those dark pink colors, they're basically calling for, from 80 to 100% probability of high flow occurring on the channel reaches in those areas, and then it sort of scales out or diminishes as you get out of that core area of heavy precipitation that was occurring. And this helps attract the forecaster's attention to these most important areas, at which point they could zoom in and go look at what's going on in particular reach of interest that might be associated with a certain infrastructure risk. Okay, so that was a very quick view of some of the forecast products which are being generated. I want to talk about some of the evaluations now that are going on and the analyses that have been growing since we sort of went into pre-operations and operational testing, and try and just give a highlight of some of the diversity of evaluations that are going on. We're not going to be able to take a deep dive into any specific variable here. To do this, we basically have been using this RWRF Hydro model evaluation package. This code is, again, it's available online. We keep pushing over versions of this into the community release version of this as we're able to document, provide test cases and example training cases for folks so that they can learn these sort of in the spirit of all the R vignettes. If you're an R user, you know what I'm talking about. And that table that you see in the lower left-hand corner then is a listing of all the different data sets that we're trying to support in terms of multivariate evaluation of the National Water Model in this R evaluation package. And so you can see there's a number of different climate variables, a number of different snowpack variables, soil moisture, as much energy information as we can get, things like evapotranspiration, skin temperature, albedo, and then of course the main thing that's been looked at is stream flow, in particular volumetric flow rate, as well as some aspects of wave celerity and channel velocity, which are coming through. And so there's functions that are written now to ingest all of this data into our data tables and provide a number of different statistical analyses associated with this. So the different model runs that we've been working on are a number of different evaluation configurations that have been developed as part of the ongoing development process. These are listed here in this table. I'm not going to go through all these, but suffice to say, for each new version of the model, we went through a structured set of tests for all these different configurations and data sets. And we're actually trying to work with NOAA on designing some ways to provide these data sets to the community. They are quite large, and so it's not straightforward just to sort of serve these through some of the normal means. So we're trying to look into some different data services, both on the NOAA side and on the NCAR side, for ways to make these retrospective model runs that are done in these evaluations more publicly available. So I'll just step through a few of these. There's been a lot of focus on precipitation, and particularly relationships between precipitation errors and stream flow errors. And so there's a number of tools that have been created to look at bias structures and precipitation, both at the point scale as well as in sort of the basin average sense, and compare that against some of the operational precipitation analyses which are generated either in real time or in shortly after real time as more particularly gauge data becomes available to create those products. We've been looking at different ways to overlay in the lower left-hand corner errors and stream flow data as they sort of map against errors and precipitation data, and look for consistencies and inconsistencies between those different error structures. Another part of what we've been doing is evaluations of soil moisture. A major change occurred between version 1.0 and version 1.1 of the model as a result of some of those evaluations, and also forecaster feedback from users of the National Water Model. Version 1.0, it was found, actually had an instability in the vertical soil moisture solution for very sandy soils, which resulted in extremely rapid drying of the soil after heavy rainfall events. And so we went through and did some numerical updates to the soil moisture solver in NOAA MP, and basically were able to minimize that error structure. And this is just an example from Hurricane Matthew of 2016, where on the left you see that shortly after, this is about a day or two after the event had fully passed through, there were areas that had sandy soils which were already drying out. And then, of course, after the model update, those areas were able to retain moisture in a much more realistic fashion. This has been tied to some of our different soil moisture analyses. And in this case, we're looking at trying to aggregate as many different types of soil moisture measurement data. Some are spatial data, some are point data, and look at different ways to evaluate the model. In this case, we're looking at some evaluations of point measurements against the model, but instead of trying to compare absolute values, basically do anomaly correlations between the model and some of the point data that's being used. And then that's what those time series are on the left, and then on the right-hand side, there's a stratification according to depth of where we have different data sets, soil moisture data sets available at depth, and looking at some of those anomaly correlation structures as well. In this particular case, just as a little highlight, the anomaly correlations on the surface don't appear to be too bad, but in the subsurface, you can see there does tend to be a propensity for more dry biases to, or low correlation values to emerge in the model. Okay, model snowpack is another important area that we've actually got some data to use and help evaluate the model. What I'm showing here is the result of some work that was done to look at some error structures in snowpack, particularly in the western United States, and particularly in areas that were above tree line, using both SNODAS analyses of snowpack, which assimilates various types of snow cover and point snow information, snowpack information, as well as NASA Airborne Snow Observatory data, which is an airborne LIDAR and imaging spectrometer system. We were able to look at some of the error structures that were occurring in snowpack above tree line in the NOAA MP model, and relate those error structures to an error in the surface resistance formulation, and make a set of upgrades to that formulation, basically correct a bug that was in the model. And that picture in the upper right-hand side is from the Tuolumne River Basin, where we had some high-frequency overpasses from ASO, capturing high-elevation snowpack behavior. And what the color scale there is the change in error in reference to the model as referenced back to the ASO data. And you can see there's largely a significant reduction in error as reference to ASO as a result of these changes. So that got rolled back into the national model, and the time series on the left-hand side is sort of a regionally averaged comparison of the different versions of the water model in red and in green versus the SNODAS product. And the green is version 1.1, and SNODAS is the blue one, showing much more consistency. Not that SNODAS is truth, but in terms of a national analysis, it's probably one of the better products we have at our disposal. We do a lot of point comparison with SNOTEL sites as well, and those are the scatter plots you see on the right-hand side of this particular graphic. And we've been able to make some measurable improvements in the behavior of the model. This is sort of combined over a very large area, a large number of different SNOTEL observations of snow water equivalent. We're also using other remotely sensed data, snow cover analyses that are coming from different data sets. These are looking at how the National Water Model was forced with different precipitation forcing data sets, national gridded data sets, as well as local radar data sets in the upper right hand and lower left corners, and then comparing that versus what the SNODAS product was saying, which is actually assimilating some of these snow cover products in it and looking at where we're getting benefit in terms of contingency statistics, say the number of hits versus misses or false positives on basically just where there's a significant amount of snow cover. So again, just another metric that's been going on. We're trying to wrap in as much data as we can to evaluate the behavior of the model. Evapotranspiration is another variable that's being looked at. It's very hard to get good data on this, but we're trying to compare against some of the Ameriflux stations across the country, as well as against some of the remotely sensed data sets which are now being produced. What you see in the lower right-hand corner is a percent bias map compared to the EC-MOD product, which itself is sort of a hybrid remote sensing and other model-based product. So one has to be a little careful on the interpretation of this, but clearly we like to look for areas of sort of large divergence between these products and looking to see if there's what's relatable about those error structures, either to the model formulations or potentially some of the forcing data that's being used. Okay, so following analysis then comes the task of calibration. So the first version, 1.0 of the model, did not have much calibration in it, but then as we started to do more and more analyses and built up the tool set associated with these analyses, we wrapped in a number of different automated calibration methodologies. And so now there's a calibration toolkit which we're trying to get documented up and pushed out for public release that basically allows us to parallelize and do a lot of independent basin calibrations within the National Water Modeling Framework and provide a more optimal parameter estimate set for operational prediction. So this has been done, and for the last version of the model, version 1.2, we were able to increase to essentially over 1,000 USGS and California Division of Water Resources headwater basins, which did not have a lot of regulation associated with them. Looks like the color got corrupted on this, but basically the orange basins you see are all the calibration basins from version 1.2. The green basins were those basins which were also used just in version 1.1. So we're getting a lot more coverage. About 10% of the land area of the CONUS has some calibration associated with it now. And then we're documenting the version over version change in model performance associated with this. I'm only going to speak to these histograms which are up on the top. These are histograms of the percent of bias in versions 1.0, 1.1, and 1.2. And what we like to see here is a stronger tendency towards that middle bin, which is plus or minus 20%, and a lowering of the magnitude of the tails. And we've been able to do that over the last few versions, particularly with respect to lowering the positive tail on this percent bias formulation and reducing a lot of the excessive large errors. You can see how those are spatially distributed in the map below, and most of those positives do come out of the western United States, where there is a lot of these stream flow values being evaluated on systems which have regulation down below them. And so you can see, like on the Rio Grande River and on the Colorado River and many of those areas, does tend to be quite a bit of high bias, but we're not representing the diversions that are coming off those rivers as well. So there's a little bit of untangling to do in terms of that model behavior, but we have a framework now that tracks this model performance version over version. You can do the same thing with correlation. So this is just basically correlation of daily stream flows. And as we've moved from version to version, you can see those histograms shifting much more over to the right to the higher correlation values. You can see on the map there's a couple of very large bubbles with very low correlation values, and those are largely associated with gauges that we don't have information for, like on the St. Clair River connecting Lake Huron and Lake Erie, or down on the Appalachia, I can't ever say that word, coming off the Mississippi River base. Mississippi River is a big diversion that we don't represent as well. So again, just another way to document version over version performance. There's a variety of different real-time statistics that are being tracked as well. And I'm not going to go into a lot of detail with these, but we're looking at a lot of regionally average statistics by river forecast center regions associated with different forecast configurations. We're showing peak flow error box plots in the upper left, and then peak flow timing errors in terms of the hours in the lower left. In the upper right, we're looking at medium range forecast skill as a function of lead time and how that tends to drop off with respect to correlation as a function of lead time. And then percent bias, you can see for that medium range forecast broken out by river forecast center in the lower right. For most river forecast center regions, we do tend to have a little bit of a dry bias coming from those medium range forecasts, which does stand in contrast to what we see in the short range forecast. So we've got differences in precipitation forcings propagating into the model and the different error structures that result from that. Of course, we can go in and create maps of these for a short and medium range as well. Again, basically the same kinds of statistics, bias overall, peak stream flow errors, short range, overall stream flow bias, and root mean squared error here for the medium range forecast as well. And all of these here, these spatial maps, are where we have these USGS reference gauges. So we're trying to look at the model behavior as it's unimpacted by some of the water management that's going on. There's a lot of work that's been going on with data assimilation. It's really a significant enough topic that I don't have time to go into it here, but we've been doing a number of different experiments looking at some different data assimilation methodologies. We're currently just doing a very basic nudging methodology to ingest real-time US streamflow data into the model, and then doing some comparisons of the model performance in an open loop version versus sort of a data withholding experiment versus a full data assimilation of what we would get if we assimilated all the data we have, and then tracking those performance metrics over time. And then the last thing that has really been a focus of evaluation, especially more recently, has been inundation. And so both within special high-resolution configurations, the so-called hyper-resolution configurations of the water model, as well as with some of the post-processing products which are generated with National Water Model output, there's the ability to generate inundation surfaces. This is an example of a hyper-resolution output from Hurricane Matthew of last year. And then overline that with either an analytical method for doing flood inundation or some remotely sensed methods from the VEERS platform, which is a passive microwave sensor, that we're trying to look at where some of these flood inundation products are agreeing or disagreeing. And this is just an example of some of the sort of hit, miss, and overlap analyses which happened during Hurricane Matthew. The last thing we're trying to do with this then is move all of this verification information into a web service platform, or basically a web mapping service, so that particularly forecasters within NOAA, but as well as a broader range of folks can access these historical forecast statistics at all these locations. And so we're migrating all of these forecast statistics and the kinds of information that I just showed you into this web mapping service, and we hope to be able to release that in a little bit, maybe in the next month or two, as that project starts to wind up. Okay, very quickly I'm going to talk about what was done with Hurricane Harvey. Obviously this is a massive event, very unprecedented in terms of some of the peak of rainfall amounts, the duration that it occurred, and essentially for hurricane behavior it was a very interesting one where we had a storm essentially stall for several days. This is a set of slides that was put together largely led by the National Water Center and the Office of Water Prediction following Hurricane Harvey, and what was created basically on the fly during that event. There's a lot of people contributing to this. Professor Maidment at the University of Texas at Austin had a very large hand in motivating sort of the development of a lot of these projects or products, particularly in his interactions with the Texas Department of Emergency Management. There's a lot of interactions with FEMA as well, and so it's really a good coming together of folks to try and sort of tease out as much value as possible from the water model, recognizing that it really hadn't been used explicitly in an event like this in the past. This is just a map of rainfall from the event. I think most folks are aware of the magnitude, over 50 inches in some locations in and around the Houston area of Texas. The Weather Service actually had to change its color scale for precipitation because of the large magnitude of this event. And here's some of the experimental products that were created by the Water Center. A lot of this work was led by Fernando Salas and some of the geospatial data set development teams at the National Water Center. This is basically a product which looks at the time in a forecast cycle for rivers to exceed their bankful stage, sort of mapped out across the Gulf Coast region. And you can see this ranges from the short term 1 to 2 days all the way out to 5 to 7 days as these areas further east of the core hurricane area near Houston got impacted by the storm movement. You could generate this for any number of different forecast cycles in that medium range forecast that we talked about. This is then just an animation both of a medium range forecast on the left and the analysis cycle from the model on the right, sort of a self-validation, if you will, of the model, looking at where different flood thresholds were being exceeded. And this purplish color that you see here is basically where all these river systems exceeded a major flood threshold that was defined by the Water Center. One of the things we learned from Hurricane Harvey was that there was a lot of cycle-to-cycle variability in each one of these forecast cycles, and it really highlighted the need for an ensemble approach to mitigate the impacts of high cycles and low cycles, which were being driven by just subtle shifts in hurricane track or the intensity of a given heavy rainfall band coming from the hurricane. So this is just two different river systems, the Neches River, which is east of Houston, and the Brazos River, which is immediately west of Houston, and some of the different forecast time traces that existed during the event, and then how we were able to take an ensemble average of those and mitigate some of the more extreme behavior that occurred. The yellow line there actually is what was available in real time from the observations. You can see they jump around quite a bit. We haven't updated with the final data set from the USGS here, so I'd imagine after the fact a lot of those jumps have been reconciled as they were dealing with issues related to measurement and rating curve adjustments and things like that. A lot of evaluations occurred here in relation to just validating against storm reports as well that were filed during the event. We were able to provide some guidance in ungauged locations. Many folks may have heard of the retirement center, you can see, which is actually flooded there in the upper right-hand corner. And the water model in its short-range forecast actually did provide some lead time for the nearest river system that went right by this retirement home in this. This is sort of after the fact of validation. We weren't able to actually utilize this information in advance to help with that, but the idea is that as this kind of forecasting system comes online and people get used to it, there would be a more proactive use of the information. Flood inundation, again, another key aspect here. These are some of the flood inundation maps that were created by the National Water Center, University of Texas, and folks using the hand methodology. On the left is a snapshot at one time. On the right is sort of a maximum inundation extent compiled over all times from the model. So you see a lot of different areas being inundated in and around the Houston area. And then we've also been able to set up a hyper-resolution run for Hurricane Harvey in this area. This is a 30-meter model animation that you see on the left, looking at basically representing a number of different flood generation mechanisms, from dispersed flooding from overland flow to sort of more of the riverine flooding as well. And there's a lot of work going on to evaluate those. Okay, going to try and wrap up here. 2 slides left. Some of the new developments then are as follows, based on what we've been learning and what's coming down the pipeline in terms of new releases. Really the highest priority in the next version is to improve this representation of overbank flow and its coupling with the overland flow fields to improve the inundation simulation as well as channel propagation characteristics. The Hawaii domain for the National Water Model will come online in the next version. There is a lot of work focused on improving forcings in terms of providing either bias correction or different downscaling methodologies for the forcing data sets that are being used. There's a number of different physics processes which are being looked at, some of the shallow groundwater representation, particularly snow albedo and some of the rain snow partitioning that's occurring. Some water management. We won't see a big change in water management in version 2, but there will be a number of different hooks which are created to begin to ingest water management information, which will come online in future versions. And then there's some other activities related to parameter estimation and calibration, as well as some initial coupling to coastal processes. So these are all things that are going to be worked on in some significant ways with the next version of the model. And so folks who are working in these areas are certainly welcome and encouraged to get in touch with the Water Center, the Office of Water Prediction, or our group here at NCAR to collaborate on those. And then lastly, I'll just mention that there's a number of different training and outreach activities going on associated with this. CUAHSI is now co-sponsoring 2 training activities a year for the WRF Hydro National Water Model System. Those happen here at NCAR using sort of hands-on computing facilities. We've been doing some training at the National Water Center for NOAA staff. We continue to host a lot of students who come and visit NCAR for various projects as well. We've got a lot of updates going on to the website and the training materials as a part of this effort. We've started a new email ticketing system for responding to requests for support for the model, and we're going to set up a user support list, email listserv as well. And then probably the main thing is that we've been working with CUAHSI and some other folks on essentially containerizing the code, which will help folks with porting of the code to their local machines. And we've been able to validate that this works for sort of sequential and parallelized versions of the codes. And we're going to release this with our 2017 October release of the code, which also will merge together the National Water Model with the community version of WRF Hydro. So it'll sort of go back to having one version of the code for all of these releases. And with that, I am happy to take any questions and definitely thank everybody for their interest.
Okay, thanks a lot, Dave. Let's all clap once to thank Dave. We have a lot of great questions. We have a little bit of time, so I'm going to moderate them as best I can. And I'm going to kind of group these in a couple categories. So the first sort of question and follow-up, because I somewhat know the answer to this, is about how or if the river network formulation interacts with the diffusive routing grid, and then what the implications of this interaction or not interaction might be.
Yeah, that's a great question. I tried to allude to that a little bit, but I didn't provide a lot of specific detail. In the current version 1.0, 1.1, and 1.2 that we've released thus far, that is currently a one-way coupling from the diffusive wave overland flow into the channel. But there currently is not a formulation for kicking overbank flow out of the channel from the NHD network to the landscape to interact in a two-way sense with the diffusive wave. And there was a reason for that, and it goes back to that issue of not having the 250-meter digital elevation model fully harmonized geospatially with the location of the NHD plus vector network. With version 1.2, that vector network DEM harmonization is complete, and now we are able essentially to do that two-way coupling in a physically realistic way. However, that is not active yet in version 1.2. That's being worked on. That two-way interaction is being worked on for the next release of the model, which will get committed in the springtime of 2018.
Great, thanks. So then there's a couple questions around calibration. And one, there's some questions about what parameters were calibrated. There's some questions just asking for more detail on the calibration process. And then finally, there's some questions about the calibration approach, and that is using the historical analysis and a more traditional calibration approach to adjust parameter sets for the more operational forward forecasts. And I was wondering if you could, I know that's a lot of pieces to unpack there, but if you could comment more on that.
No, those are all really good questions. They do come up quite a bit in these discussions. So we calibrate a number of different parameters in the model. Some are specific to the land surface, column land surface physics, things like the infiltration and drainage scaling factors in NOAA MP, soil water retention capacity, hydraulic conductivity, some of the vegetation structure information, and also in some of the routing terms, things like what's the minimum retention depth of water before we allow overland flow to occur is another one. So those are all parameters which we have subjected to some pretty basic sensitivity tests and have said, well, these are the ones that tend to be most sensitive over a range of behaviors and over a range of catchments. Now, there's obviously, in a country the size of the U.S., there's a lot of variance with that, but that's our starting point. The calibration methodology that we've been using so far is it's a supervised calibration. It's the dynamically dimensioned search method, which was developed by a group in Europe that's been used in a number of different ways for model calibration. There are other methods which are available in R that we have begun to utilize. The reason we went with DDS in this case was that it was fairly efficient in a time to solution, and we did all this work in sort of a very short time frame, basically a matter of weeks to months, to get something implemented for the sort of first three versions of the model. So we needed something that was going to be fairly fast. And so we adapted DDS to interact with all of the error metric calculations that we had wrapped in RWRF Hydro. And basically we're calibrating stream flow, right? We're calibrating to minimize stream flow error behavior in the model by adjusting those parameters. We do track a number of different metrics, model performance metrics related to stream flow, and there's a short list of them there. There's about 13 different metrics that we track related to stream flow behavior right now. But what we're actually calibrating on is a modified Nash-Sutcliffe value, which is a linear average of the normal Nash-Sutcliffe value and a log transform of the Nash-Sutcliffe, so that it is not as oriented just towards sort of large magnitude peak flow conditions, but also maintains a balance with base flow error conditions. And so, yeah, that's what we optimize on, is that transform Nash-Sutcliffe using the DDS method. We use headwater catchments from the USGS reference network data set, Gauges 2 reference network data set for calibration. And really, I think the biggest challenge that lies out there again then is how we regionalize those parameters. And so far, we've been regionalizing based on some predefined ecoregions, which are utilized by the EPA for a number of different applications. And that's an area right now where there's been a lot of discussions with academic collaborators as well as folks within the Office of Water Prediction about exploring a number of different regionalization methodologies. So that's, without going into a lot more detail, that's the quick and dirty on calibration.
Great, thanks. That was a lot of additional information. So the next kind of group of questions revolve around groundwater parameterizations and how much there is, sort of maybe you could expand on the simple groundwater delay time or groundwater parameterization for base flow, and then what the plans are for having either a leakage into groundwater or other groundwater components.
Yeah, so as I mentioned earlier, our basic conceptualization here is a 2-meter soil column, which can saturate, and when it saturates, we can move water laterally through that, but it is a leaky soil column, and that water does leak out of that soil column into essentially a bucket. So we have a bucket model which is handling the base flow processes into the river channel network. There is one bucket per NHD plus catchment. So each NHD plus vector, river vector reach has one catchment associated with it, and each one of those catchments is a base flow bucket. The formalization of that bucket is a simple exponential model. Basically, it fills and discharges as an exponential function of the amount of basically how full the bucket is, and then there's a spill formulation as well for the bucket. It gets tuned empirically using scaling factors that are applied over larger catchments where we have stream flow data. There's obviously not one stream flow observation per NHD plus catchment, so within an entire watershed, we have many NHD plus catchments and therefore many buckets, and then we can go through a calibration. We'll apply a scaling factor to the buckets within that watershed accordingly. And so the parameters that we calibrate with those, which are wrapped up into the rest of the automated calibration, include the exponential factor as well as the maximum storage capacity of the bucket. That is itself a one-way coupling. It receives water from the soil column and it discharges water to the river channel. There's no feedback at this point in time from the river channel back to that conceptual bucket model. So that's the way things exist now. Moving forward, there has been some discussions in exploring other parameterizations for those bucket models, including a slightly more sophisticated wedge aquifer model, which could be used in there. But ultimately, the idea behind the national water model is to be doing this in a more physically consistent way. And then we're talking about two-way coupling between the river channel network and the soil column, or a more sophisticated physics-based groundwater model. So those are on a slightly longer development track in terms of what is being done. We really couldn't justify a robust two-way coupling between the soil column and the river channel until we had two things. Again, that harmonized river network and DEM, so that we knew where the river reaches were better located with respect to the topography of the model, but also before we had bankful depth estimates from the model so that we could actually have a physical height of flow and of depth of these channels into the soil structure. So the National Water Center has been developing a number of different bankful estimate products lately and doing some assessment of those against a lot of USGS survey data. And so there's a first generation of bankful depth estimates which has been generated, and so that'll get wrapped into the next version of the model along with the two-way overbank flow coupling. We won't do the two-way subsurface coupling yet, but it sort of sets ourselves up for doing that in future versions.
Great, thanks. A lot of information in there. So the next kind of group of questions, and I think this is going to be about our last set, are a little more detail on the release schedule and the harmonization between the WRF Hydro version that's in the National Water Model and the WRF Hydro version that's sort of publicly available. And then there's an interesting follow-on question on that about if there's any independent peer review or public review or comment for the National Water Model.
Yeah, so good questions again. With the latest version that we're working on right now, we have again unified what we called traditionally the community version of WRF Hydro and the National Water Model version. The reasons that those diverged sort of over the last 2 years were basically due to the extremely rapid time frame of development that the water model got put on. And there's a lot more options that are supported in WRF Hydro than exist just within the National Water Model configuration. So the National Water Model is a singular configuration of WRF Hydro, whereas WRF Hydro has a number of different options, different land surface models, different routing methodologies, so on and so forth, different spatial frameworks that could be used. But due to the deliverable timelines for much of this work with the National Water Model, we basically had to push ahead with a version of code which met all of those requirements. And finally, over this past summer, we've had some time to come back and harmonize all these together into a unified release. So what will be released here in a few weeks, basically right after this upcoming CUAHSI workshop here at NCAR in a couple weeks, will be that first unified version. It will include version 1.1 of the National Water Model, which is the currently operational version, and that's what NOAA authorizes to be released, is the currently operational version of the model code. Reason for that is version 1.2 technically isn't frozen yet, and so it could change significantly, and so they don't want basically development code floating around out there, which makes sense. But version 1.1 of the National Water Model is going to be, or is now, harmonized with the rest of the community version of WRF Hydro, so that this is available to the broader community and that folks can start using that. That said, there's a lot of those support tools which were built for the National Water Model, which we're also trying to document and get into a format that we can actually support a large number of people with. And so not all of the supporting tools are going to be released at the same time, but we're going to try and push as many things out as we can as possible. Things like the GIS data processing tools, things like parts of that forcing engine, obviously the WRF Hydro model evaluation tools are all publicly available in various forms now and will be updated as much as possible along with the code released, which is coming up. In terms of peer-reviewed publications, you can ask any operational model developer, and this is always a challenge, particularly in an extremely rapidly development time frame. And so we're working on a number of publications now in various aspects of the model physics, the underlying geospatial data sets, the first few generations of model performance, some of the sort of ancillary products of the model as well. And so there's a number of manuscripts in preparation, and we're trying to push this stuff forward as quickly as possible for submission and distribution, because we know that folks definitely want to be able to review and cite things in their own work. So we're doing as much as we can in that regard. That said, the data sets that are produced by the National Water Model operationally are all publicly available. Each version of the code is publicly available. The data sets are publicly available. So, those are available for the broader community to be interacting with already. And I think sort of in the spirit of many new publications like GMD and places like that, where models like this get published, those criteria for having sort of an open and transparent sort of sets of data set for people to look at and evaluate are already happening operationally. But in terms of the papers, yeah, we're trying to move those forward as much as possible. We have prioritized, obviously, the support of these tools for the community so that they can access the code and access the tools to use them, though, as well. So we want to make sure people can use this and that we're not holding back that support until these publications happen.
Terrific. All right, well, let's all thank Dave one more time. Everybody can clap virtually at their desk, well, not clap virtually, but clap at their desk, virtually thank Dave. Remember, this is the third of 4 presentations. They've all been terrific so far. Thank you all for the tremendous questions and great attendance. Laura Condon of Syracuse University is our final speaker next week, same time next Wednesday. So thank you all, and I think we'll conclude the broadcast.